Okay, so we're going to go over some ways that we can figure out how old things are. Relative rock dating and absolute or radiometric. Nearly all of you have already done this through your team activities, but this is just to make sure that everybody's got it covered. Okay? Two people, James Hutton and Charles Lyell, are kind of the first people that started to come up with this. James Hutton is known as the father of modern geology, and they really helped, and most of what they did was the relative rock dating. Okay, so there's some information about them and who they were. They're kind of the two main people who started looking at how we can figure out how old the Earth is and how old stuff on the Earth is by looking at things like the layers and how rocks are associated with each other. Okay? Okay, so we're going to look at relative rock dating or relative time, and we're going to look at absolute time or absolute rock dating. So relative rock dating is where we can say what things are older or younger than others. For example, she is older than he is, or she was born first and he was born last. Okay, that's relative. Absolute is where we know exactly how old they are. We get a number for how old they are. Or she is 21 and he is 19. Okay, those are kind of examples of how those two are different. And we're going to take a look at these again. Okay, so relative time or relative order, these are the three concepts or three laws that we've used. The law of superposition, the law of cross-cutting, and the law of inclusions. Those are the three laws that we will have to, that you'll have to know and be able to use, and they're the three that we've talked about. Okay, so to review, the law of superposition. It says within a sequence of undisturbed sedimentary or volcanic rocks, oldest rocks are at the bottom and youngest at the top. So we get younger as we move upward. Okay, oldest are at the bottom, youngest are at the top. And you've all seen that before. This is just a review. Okay, so you have a drawing. I want you to label where the oldest is and label where the youngest is. Okay, label where the oldest is, label where the youngest is, and hit submit. But we're just looking at layers.
Don't make fun of my spelling, Mr. James.
Why? Because it's listed on your question of how to spell them.
Yeah, on youngest.
I don't forgive spelling errors if I give you the words and you just can't bother to copy them.
Will we get a score for penmanship?
On this, no, because it's really hard to write.
Okay, good.
Okay, I've got quite a few, and by looking at them, everybody, as far as I can see, is doing just fine. So we'll just pick one and show it. Okay, so here's one example. The youngest is on top, the oldest is on bottom. So you did a great job of that. Even if we have something, like this might have been where a river was, that's eroded all of that away, we can still say that the oldest is on the top and the youngest is on the bottom. Okay, so let's continue on to our next law, which is the law of cross-cutting. Okay, so this is where a disrupted pattern is older than the cause of the disruption. Okay, so we've got this pattern, this cross cuts. That means this whatever was here before is older. Same thing is true here. We have all of this, and this comes in and it disrupts it. That means this was older than this. Okay, or an intrusion is younger than the rocks it intrudes. Okay, and we can have batholiths, which is this is an example of a batholith. It's just the igneous intrusion that's larger, whereas a dike is an igneous intrusion that is thin and cuts across. Okay, those are our two things, batholiths and dikes, and they both come into play in the cross-cutting law. We can also have things like faults, where we have a crack and things start to move along that crack, is where another type of cross-cutting. Okay. So here is a question for you. Label the dikes A, B, and C, oldest to youngest. So we've got 3 dikes, A, B, and C. Label them oldest, youngest, middle. I don't know what they are. You tell me. You tell me oldest, youngest, and middle. So you should label 3 things. Oldest, youngest, and middle. Don't worry about the rocks in the back. Just label the cross-cutting parts.
I'm sorry. There you go. Sure hope you can read it, Mr. James.
Okay, looking through this, I am seeing you're doing well. Everyone that I've seen so far has been good. Okay, so let's just take a look at one example. Again, maybe. There we go. Okay, so we've got oldest as C, middle is B, and A is the youngest. Okay, again, whatever's on top is going to be the youngest. Whatever cuts the thing, whatever's cut by it is older. So A cuts B, which means A is younger and B is older. And B cuts C, which means B is younger and C is older. So it has to be oldest, middle, youngest. Okay, and you all did well on that. So let's continue on to our law of inclusions and do a review of that as well. Maggie, you can go. Okay, so inclusions are fragments of other rocks contained in the body of a rock, and those must be older than the host rock. For example, we've got pieces of granite in here. Okay. Those must be older than the rocks that they're inside of. Okay, so here's another example. Xenoliths in granite are older than the granite. Okay, these inside of our granite must be older. And pieces of rock inside of a conglomerate have to be older than the conglomerate. Okay, they couldn't, just like we talked about, the ingredients in a fruit cake have to be older than the fruitcake, right? Because you had to go to the store and buy them, take them home, and then make the fruitcake. So they have to be older. Okay, so you have this example. Which is older? Rock B, rock A. Yes. And you can write out your answer, you can circle your answer. Which would be older, rock B or rock
Are those
A?
little things rock A?
So colors are the same kind of rock. Same color is the same kind of rock. Yeah. Quick.
Oh, I have to submit it.
Okay, it looks like everybody's pretty much responded. I'm going to share this one with you. Okay, rock A is older because it's in rock B. Right? Those pieces couldn't have shown up inside of rock B unless they existed before rock B did. Okay, so rock A is older. And everybody that I saw had that correct as well. Okay, so let's take a look at this. So with those laws, we can look and we can figure out what happened here. Okay, there's a lot of stuff going on here. We've got batholith intrusion, we've got a dike intrusion, we've got some slanting rocks, we've even got this stream that's coming through that's eroded a lot. But just with these laws that we have, these three laws, we can figure this out. So what I'm going to show you next is a lot of stages of this formation, but we'll be able to see how those all form.
I have a question.
Yes.
If it's slanted, how do you know which one's older?
Okay, good. So generally when things are slanted, they don't flip all the way over. Okay? Sometimes they do, but generally they don't. So which one would we expect to be older? This one, right? We'd expect to be oldest and youngest. And on anything that we do, that's going to be the case. It's not going to flip all the way over. There are situations where it can flip all the way over, but we won't worry about any of those. And there are other tricks to figure that out, or techniques to figure that out. For example, I might grab you this rock and get asked about it. If we are talking about sedimentary rocks, they are generally formed in water. So sometimes when those sedimentary rocks form, the water will leave a shape on them. So this you can see is a sedimentary rock, but it looks like it's formed from sand, and that's the bottom of at the bottom of the water, bottom of the ocean or something. Okay. So if we were looking at a rock, if we find something like that, we know that that is up. Okay? So if that was completely upside down, then we know it's been completely flipped over. So that's another technique that we can use. Okay? But generally, it takes quite a bit to flip a whole series of rocks all the way over. So generally, though, we can assume that this is older and this is younger. Good question. Okay, so here's an example. We're going to go through each step of the formation of this rock, and we'll see how that process happens. So first we start with water, and we have our sea floor. Okay, and then that gets deposited. So here's our sea floor. We keep depositing all of these layers. Okay, that forms into a lithified rock. And if you remember, we had that intrusion that came in, that granite. So it comes in and it cross-cuts them. Okay, so we know these are older, these are younger by the law of superposition. And then this comes in, this batholith comes in and cuts across it. So we know that it's younger than all of those pieces. Okay, and then what we have sometimes is these rocks are removed by erosion. Okay, and we also have some tilting here. But we see that that's been eroded. So sometimes we'll see rocks that get cut off like this. That's because of that top layer. Those top layers get eroded. Okay, and then we have more deposition on top of that. And that's where we saw that Shani asked about, where we had it slanted, and then we had level rocks across it again. And you'll see, some of your examples, you've seen that. Something happens, it gets slanted, that will get eroded, and then new rocks can get deposited on top of it. That's how we get layers that don't always line up. Okay, we're going to have more deposition, and we've also got, if those rocks were removed, sometimes that gives us a gap of time that we're not certain of, right? There's erosion, takes away that record of the rocks that were there, and so we might lose some of that time, essentially. Okay, then we have our dike that comes in and cross-cuts again. It comes across, and we can see that, we know it's younger than everything that it cuts across now at this time. Okay, and so now what we're left with is we have this dike that's on the surface. Okay, we know that it went between two layers of rock, but that top one has now been eroded away. And we're going to get some more deposition on top of that. And again, we can see where, on one of our examples, we have that dike that comes up to the surface and goes level. That's an example of what's happened here. But we're now getting more deposition on top of it. And then we're getting closer to the current day, right? We've got these layers, and we got grass and a stream. And this stream is eventually going to erode all the way back down through those layers. And we end up with what we started with, okay? And so we can do things like, we can go back and say, okay, this should be this age, and we can assume that, these are the same age, and these are the same age, and these are the same age. Even if they're separated by a large distance, if our layers look the same, we can assume that they are the same age. Okay, so one more kind of practice with a couple laws and a little bit more complex for you is put these in order from oldest to youngest, just the letters, A, B, C, and D. Put them in order from what you think the oldest is and what you think the youngest is.
Can we just put them in numbers?
Yes, letters. Or you can write a number next to them. I know that too. So either give me a list of A, B, C, D, or whatever it is, or write a number next to them.
ABCD 可能就2个最原始，可以显示啊，在上面说 oldest、youngest 到标准来的。
Okay, and getting quite a few people. So this one's going to be a little bit iffy because we've all might have looked at it a little differently, and somebody might have put numbers, and somebody might have put letters. But we'll look at them, and you just need to make sure that yours, that you know how to figure out how old these are. We're seeing almost everybody finished. So let's take a look at some of these. Okay, this person gave us a number order from oldest to youngest, I think. So they're saying that C is the oldest, then B, then D, which crosscuts, and then A, which is on top of it. Okay, so check that you had a similar thing. So the youngest should be A, the next youngest is D, the next youngest is B, and then the oldest would be C.
Yeah, we did
Okay?
youngest to oldest.
C, D, D, A, or A, D, B, C. Okay?
所以这里他说 B 比 C，
Okay, we're going to move on to absolute rock dating
所以刚刚我
and
们
talk about a review of that. Okay, so remember we have these two tools, relative rock dating and absolute or radiometric dating. Okay, we're going to use radiometric dating, which is where we use this nuclear clock or the decay of radioactive isotopes. Okay, radioactive isotopes, they have a nuclei, the nucleus that spontaneously decays, which means they either emit or they capture a subatomic particle. Okay, and in one of your activities, you looked at types of decay, alpha decay, beta decay, neutron decay, and you looked at what would happen to a nucleus if that happened. So, keywords that we have is your parent and your daughter. Yes,
这个
Liz?
元素呢，它的名字就跟你一样。
Okay, so your parent is what we start with, and our daughter is what we've lost.
如果
Okay? And sometimes we can change element type. We just change its isotope, and sometimes we change to a completely different element. Okay, so let's look at this. There's three main ways, and we talked about four, but there's alpha, beta, and electron capture. So alpha particle, that's where two neutrons and two protons leave the nucleus. Beta decay is essentially where a electron or a beta particle leaves the nucleus. And electron capture is where we add an electron essentially to that.
它有两个 neutron，两个 proton 合起来。
Okay, so how we use this for radiometric dating? We know from studying these elements that they have specific decay rates, or that they decay all at the same amount of time, right? We call it our half-life, and we look at each radiometric element has a different half-life. So if we look at this section, second section here, it says, as minerals crystallize in magma, they trap atoms of radioactive isotopes in their crystal structures. Okay, these radioactive isotopes will decay immediately and continuously. So once it's formed, they start to decay, and they keep decaying until it's changed into another igneous rock, essentially. It keeps decaying as long as it stays there. Okay? And as time passes, it loses its parent and gains more daughters. So we're going to be looking at those ratios of how many parents do we have and how many daughters do we have to figure out how old that rock is. So what I want from you is answering this question. When a radioactive parent atom decays, it A, disappears, B, becomes a heavier atom, C, becomes another type of atom, or D, leaves the rock.
衰退了之后，同时会
What happens to our radioactive parent atom?
第三个是变成另外一种名字，最后一个呢是它从这个石头里面流失掉。这是最后一个。简单的就是它有一个石头衰退了，就是它这个石头里面流失掉这些东西，流失掉这些辐射，就叫辐射衰退。然后呢，这些东西呢跑出去了之后呢，它有可能会
Okay, it looks like everybody has
这
answered.
个石头。
Okay, so when a radioactive parent atom decays, it becomes another type of atom. It's either going to change type. It might go from, say, uranium to lead, or it might change its isotope. It's going to change its mass, even though it stays the same type. But it's going to change in some way. Okay, it doesn't leave the rock, because if it left the rock, we'd have no way of seeing parents and daughters, right? We've got to have that ratio of what they were before to what they become to look at. It doesn't disappear, okay? It's still going to stay there. And sometimes it could become a heavier atom, but that's not an answer that works for all situations. Okay? So it becomes another type of atom. Is that going to switch Either its number of protons,
不同的。
or it's going to switch its mass and stay the same element but be at a different weight. Okay, so a half-life. We talked a lot about half-life. We did our experiment on half-life. But it's the amount of time it takes for half of the atoms of the parent isotope to decay. And different radioactive isotopes have different and distinct half-lives. For example, carbon-14 is 5,730 years, right? Whereas others might be a billion years, or some might even be a few days, okay? 84 days, 136 days, small amounts, okay? If a rock has 12 parents and 12 daughters, a ratio of 1 to 1, we know that it started with 24 parents and half of them have become daughters. Okay, so it's gone through one half-life. After another half-life, we'll have 6 parents and 18 daughters. Okay, a ratio of 1 to 3. We always are going to keep the same number of the same total number of parents and daughters. We're just going to change how many of them are parents and how many are daughters. Okay? And so that's where we use our percentages. After one half-life, we've got 50% of the parents and 50% daughters. After 2 half-lives, we've got 25% of the parents and 75% of the daughters. After 3 half-lives, we've got 12.5% of the parents, 87.5% of the daughters. Okay, we're always going to reduce how many parents there are by half. So here's a question for you. If there's 25% of a parent atom and 70% of the daughter atom, how many half-lives have passed? 1, 2, 3, or 4?
7.
Not an option.
所以它这里就是说，现在的父母元素只有25%，然后女儿元素70%，所以它这里经过几次衰退，它刚刚每次一衰退就是减半，一开始24，经过一次之后变12，所以它这里经过几次？经过一次变50%，50。原本50，原本父母是50，再减半会变50。
Okay, still waiting for about a third of you to respond.
What did you get, Sharon?
Don't pick 2 in. Pick your 1.
So funny. I should have picked all
Still waiting for you.
You walk around and pick out.
Okay, let's take a look. Okay, so most of you said it's been 2 half-lives. So I actually have this drawn up here. This was from our experiment where we got, we started with 10 centimeters, and then we would have 5 centimeters after 1 half-life, and then we'd have 2.5. Okay, and these work well for percentages as well, because with the parent, we would always start with what percentage of the parent?
100.
100%. 1 half-life later, how much would we have?
50.
50%. No, because we're only going to lose half in the amount of time. So 1 half-life later, we're going to have 50%. Another half-life,
25.
we're going to lose half of this, so it'll be 25%. So we've had 1 half-life, 2 half-lives. So our correct answer here is 2 half-lives. Okay?
Oh.
So that's something you'll need to know is percentages and be able to figure that out.
Do they always decrease by the same percentages?
No, because in this time they decreased by 50%. Here they only decreased by 25%. But they always decreased by half of what the parent there was. Right? If we had 1,000, then we'd have 500. We wouldn't lose another 500, we'd lose whatever half of it is.
所以每一次呢，它经过一次 half-life，它原本的元素就会减半。
Okay, so here is kind of a diagram to help us to look at and see what happens with this half-life. Okay, so we have a graph, and you've looked at these graphs. We did them on our lab, we did them on our computer simulation, and you made them with our soap example. Here is also another example where the purple dots are the parent and the yellow dots are the daughter. So you can see that we always have the same number of total atoms. That never changes. Okay, it always stays the same. But we always start with all of them as parents. Okay? And then half of them would be parents. And then 1/4 of them would be parents. 1/8, 1/16. Okay? And we can see our percentages. After one half-life, we're down to, after one half-life, we're down to 50%. Okay? After 2 half-lives, we're down to 25%. After 3 half-lives, we're at 12.5%. 6.25% at 4 half-lives. And we'll never get to 0 parents. Okay? We don't ever get to 0 parents. We're always going to stay there. Okay? And we always will have half of what was there at the last half-life. Okay? Always went from 100 to 50, 50 to 25, 25 to 12.5, 12.5 to 6.25, and we're going to go to 3.125, and so on and so forth. We're always going to be having some parents around. Okay, so here's another question. After 3 half-lives, the percentage of remaining parent atoms should be what? Take a moment to think through what would it be at 1 half-life? What would it be at 2 half-lives? What would it be at 3 half-lives?
Bird.
CJ. Okay, after 3 half-lives, the percentage of remaining parent atoms would be what? They'll wait until about 1/4 of you to reply. Okay, let's look. I still got some of you that haven't responded, but we'll look at what we've got. Okay, so after 3 half-lives, the percentage of remaining parent atoms should be 12.5%. And 60% of you did that correctly. There's 20% of you that didn't answer. 10% of you, which is 1 or 2 students, said each of these numbers. Okay? So how many do we start at 0 half-lives?
20.
100.
100.
Okay, after 1 half-life, what percentage of parents would we have? 50. After 2 half-lives, 25. After 3 half-lives,
6.25.
after 4 half-lives.
6.25.
Okay, so you've got to become familiar with those. Okay, this is what we call an exponential decay. It never goes to 0. This is an example of a linear. And if you look at your graph from your lab, you'll notice that they do have that curve to them. Okay, they'll never go to 0. And that's because it's an exponential decay. Okay, so here's an example of uranium-238 to lead-206. Okay, and we can see this takes quite a bit of time. Lots and lots of decays. Uranium becomes thorium, back to uranium, thorium, radium, radon, polonium, lead, bismuth, polonium, lead, bismuth, polonium, lead, until it stops. Okay? But what we know is that half-life takes a certain amount of time. Okay, there might be lots of steps in between, but we know from a radioactive parent to a stable daughter. What that means is this one down here will not decay anymore. Okay, it will no longer go through radioactive decay. And that's what we look for when we talk about our isotope sequences. We have a parent to a daughter, and that daughter has to no longer decay. There might be a lot of little steps where all of these little steps in between will continue to decay, but we know that from here to here, this will no longer decay. We have a specific half-life or amount of time it takes for half of those to do that. So here's an example. Uranium to lead. So uranium to lead 206 takes 4.5 billion years. Uranium to lead 207 we know takes 713 million years. And thorium to lead 208 we know takes 14.1 million years. So we've got all of these different tools that we can do this. Potassium 40 to argon 40, 1.3 billion years. Rubidium to strontium, we know is 47 billion years. Okay, so we have all of these tools and all these different types of isotopes that we can use. So your last question is, what is a half-life?
Half-life 是什么？
是那个急性衰退。
你说衰退，是衰退率。
That is not a heart. You want to try it?
Okay, I'm going to share a few of these with you. Let's take a look at this one. A half-life is the time it takes a parent atom to become a daughter atom. Okay? I agree with that, but let's be a little bit more specific. The time it takes for
50%.
half of the parents to become daughters, right? That's why this is more like a life of an atom, right? But we need that half in there. It's the time it takes for half of the parents to become daughters. Okay? So we want half-life. Life tells us how long it takes. Half tells us how much we're talking about. We're talking about half of the parents becoming daughters. Okay? Let's look
What
at...
happens when there's no parents left?
Okay, it's always going to have some parent left. It's just going to be smaller and smaller and smaller percentages. That just tells us how many half-lives have been, right?
There will never be zero parents?
Correct. Because we always decrease by half. Okay, half-life is when it's only decays a certain amount. What would that certain amount be?
50%.
Half. It's the amount of time it takes for half of the parent to decay into daughters.
You should put mine up there.
Yes.
Just asking, what does half-life have to do about getting the age of the rocks?
Good. So let's look at this one real quick. Half-life is how long it takes for half of a parent atom to decay into a daughter atom, and then half of that, and so on. Good. So if we know, for example, that we started with 10 parent atoms, we now have 5 parent atoms and 5 daughter atoms, we know it's been one half-life. And for that atom, we know it takes 300 years for one half-life to happen. We know there's been one half-life, so we know that's 300 years old. Okay? And that's how we use that. Let's say, again, this is 300 years per half-life, and we know that we've had 2 half-lives. How old must this rock be?
1.5.
Where'd you come up with that?
Oh wait, never mind.
600 years.
We know it's. How do we know it's 600 years, Josiah?
Because it's been 2 half-lives.
Right, it's been 2 half-lives, and 1 half-life takes 300 years. I still need to talk to you to figure out where you came up with 1.5. Because that confuses me. Okay? So you can use those tools. And